Catalyst Club. My name is John Stencil, current president of the local Catalyst Club. I'm pleased to see a lot of old friends here, young friends, and also some new faces that we haven't seen at these meetings. I think that today we have a good program. We have a number of items that I would like to mention before we start, just to take care of things. In terms of people that may have driven and parked their car in the parking structure right next to the hotel, if at some time during the break this morning or at noontime you give me your parking ticket, and I will get those stamped so that you can, when you drive out, just hand it to the person at the ticket booth. The sessions this morning will go until noontime. We will be eating right next door. We're here for lunch. The restroom facilities are out the room and all the way down to the left around the corner, down the hall. If all of you have seen Fred Tungate out in the front, I'm not talking to you, but if you haven't seen Fred Tungate to pick up your name tag and or pay your entrance fee, please do so sometime this morning.
Thank you very much.
During the last year, our Tri-State has had a very successful and very interesting year in presentations. Some of you who are new here don't know how the Tri-State is set up, and I would like to just describe a couple things about that. The Tri-State consists of clubs in the Ohio, West Virginia, and Kentucky regions. We have a number of active people in various towns within this Tri-State area. And just to give you a flavor of our yearly activities, last November we started out in Lexington. We had a talk by James Idle, and oxidation in retrospect and prospect. He was to see a Pettit lecture. Then in December we moved on to Ashland. John Butt gave a talk there on catalyst deactivation and chemical process dynamics. In January, we went on to Charleston, West Virginia, where Jack Lunsford gave the Burr lecture entitled Methane Activation Mechanism in Active Sites. In February, we went on to Louisville, where George Meitzner gave a presentation on the structure of supported bismuth bimetallic catalyst using XAPs. In March, we were in Cincinnati, where John Cleave gave a presentation on reaction studies with temporal analysis of products reactor. And finally, we're back in Lexington. So we've done a full circle. We've gone through 5 different cities. I've been able to and have had the pleasure to attend each one of these presentations. And I'm glad to see that we are coming to a successful end to our season. One other brief mention, the Tri-State Catalyst Club will host the 1991 North American Catalysis Society meeting. And if during the day or in the upcoming months you have suggestions on or ideas of programs for this 1991 meeting, please see myself or Bert Davis. A number of you have sent in suggestions. If anybody else has them, please send them to me. So with that, I would like to introduce the chairman of the morning session. Vernon Millett is not here, so Jim Hoffman is going to take care of the morning session. Jim?
Thank you, John. Our first paper this morning is from W.R. Grace, entitled Structure and Selectivities of Low Unit Cell Faujasite by Alan Pieters, co-authors Chang, W.C. Chang, and K. Rajat. Alan?
Bert's got his camera zeroed in. I've got to get a haircut. Anyway, I'm going to talk to you today about some work that we've done at Grace. A lot of people are working on why low unit cell size USY sieves make high octane gasoline what selectivities that involves and how that comes about. And I'm going to talk to you about some of the work that we've done with that. Structure and selectivity to linear cell faujasite. It's Wu Chang, Mike Shatlock, and the NMR company. This is sort of a background slide. These Bartholomew and others have shown that there's weak and strong sites in USY type materials. And Dempsey, especially Dempsey, suggested that acid strength is related to site isolation, which has been something that people have been working on now for about 10 to 20 years. Pine and others showed that basically octane selectivity is related to a high silica-alumina ratio in the faujasite is related to relatively low numbers of aluminums per unit cell. And co-selectivity has a similar relationship to unit cell, although it's not the same relationship. One of the problems is people know pretty much about the structure of faujasite, but they don't know exactly where the aluminums are. They know what the structure, they know the oxygens, they know where the hydrogens are more or less. They know where the silicons are, but the XRD and other techniques have not really shown where the aluminums are. Litma and some others were able to use magic axial spinning NMR to identify silicates in different with different coordinations of aluminum. And this provides an indirect probe for the kind of aluminum siting that you have. For example, to what degree you have a silicon with, say, 2 aluminums next to each. If you have a silicon attached to 2 aluminums, you get 1 shift. 0 aluminums, you get a different shift. 2 aluminums, for example, in that top slide. And it's 4 means that you have a silicon attached to 4 different aluminums through an oxygen bridge. So this gives you some way of probing where, what kind of aluminum distributions you have in the zeolite. The top one is a faujasite X with a relatively low silicon-aluminum ratio. You notice there that there are still some silicons that don't have any aluminum directly connected to them. The one at the bottom is a more normal, typical faujasite. Faujasite consists of hexagonal prisms. They're connected together. The hexagonal prisms can contain 6, 5, 4, 3, 2, 1, or 0 aluminum atoms. There is a statistical mechanical procedure that you can go through and you can calculate in any assembly of these prisms what's the most probable distribution of those prisms. And if you do it the same way, using Lagrange multipliers in that same business. In any event, if you do that, you can pretty much calculate what a aluminum distribution in a random, in a faujasite would look like if there were no energetic, no avoidance rules, no energetic constraints or anything else. If you do that, what you do is you get that solid curve. This is the curve for a silicon attached to 4 aluminums. As the number of silicons per unit cell, there's 192 total atoms in a unit cell. As the number of silicons increases, the number of silicons attached to 4 aluminums decreases. And in fact, it decreases faster. The data points are experimental data points, which are taken from the literature. About a third of them were determined in our laboratory. It turns out that the silicons attached to 4 aluminums, that kind of silicon decreases in population faster than you would expect based on what one might call a most probable statistical distribution would give you. The same thing happens with silicons attached to 3 aluminums. It goes up, and it initially goes up to compensate for the lower distribution of silicons with 4 aluminums, and then it goes down, drops below the line, and goes to zero at somewhere around 150 to 160 solutes. There's some points that are above what looks like the curve, and I'll talk about those a little bit later. Those are probably unreal in the sense that you're seeing apparent silicon attached to 3 aluminums, which is not really that. Those are mostly obtained by hydrothermal elimination. This is silicon attached to 2 aluminums. In this case, the curve goes up, but then it approaches the theoretical curve. So we would say that aluminums can be attached to each other. In other words, you can have a silicon attached to 2 aluminums. You can have a binary site, and there is no avoidance rule for this binary site. That is where you have an aluminum, silicon, aluminum. Again, similar situation for silicons attached to only 1 aluminum, and you have a similar situations for silicons that are essentially attached to 0. The result of that is that in USY, where you have a silicon-aluminum ratio of, say, 6 or higher, that you only have 2 kinds of sites. You have binary sites, where you have an ALO, SiO, Al. You have an isolated site where you have an aluminum with no aluminum secondary neighbors. You don't have any sites of higher order. You don't have any sites where you have a silicon, where you have an aluminum attached to 2 other aluminums through a silicon. In other words, they simply don't occur in USY type materials. This is what, if you go through that, in other words, since we have that calculation, we can actually correct it for those rules. We can go through and we can plot what the actual distribution of these different kinds of sites are. And your straight line, of course, is the number of aluminums per unit cell, which is circles, and then you have the number of isolated aluminum sites, and then you have the number of paired aluminum sites. And the interesting thing is that the site isolation occurs very early. And it occurs early partly because of that avoidance rule that the 3s and the 4s tend to be avoided. What's interesting about that is that octane starts at about 2430, and we've already got a lot of isolated sites. So the attempt to correlate octane with site isolation, it's not obvious that can work. This is a little clearer picture. The circles, again, are the number of isolated aluminums per unit cell. And again, you have octane begins where you have a maximum in site isolation. Now, as what happens is the number of paired aluminums, the binary sites, decrease, and it turns out if you plot that decrease against coke yield, and that coke curve is taken basically from the Roger Gauquin paper, what you see is that the 2 are almost superimposable. In other words, what that would suggest, although it certainly doesn't prove, is that there's a correlation between coke make in a faujasite or in a catalyst and the number of paired aluminum sites. That is the number of sites where you have 2 aluminums, 1 silicon away from each other. How do you correlate? How would you get the octane correlation? Well, what we did was we thought to ourselves that all of the aluminums are active. So any aluminum in that unit cell can crack. And what we thought was that the binary sites would be hydrogen transfer sites. So if we take the total number of aluminum sites and divide them by the binary sites, which are the hydrogen transfer sites, we might get something that looks like an octane curve. And it turns out that that's exactly what you get. You get something that's very, very close. The squares are is an octane curve, and the circles is that total aluminum site divided by the binary sites. What that implies is that octane selectivity is a lot like structure sensitivity in the kind of thing that Boudard talks about in noble metal catalysts. We do the same thing for motor octane, although frankly, motor octane doesn't change much, it's probably not. But it has a similar slope. What we did, we took some, the octane didn't fit exactly, and so we thought that if we, Bartholomew has recently published a paper in which she suggests that isolated sites might be 5 to 6 times more active than non-active. Strong sites are maybe 5 to 6 times more active than weak sites. If you associate isolated sites with strong sites, then you can do this, and rather than just have site densities, you can talk about total activities and binary site activities. And if you do that, you get an almost exact match in the slope between the octane curve and that selectivity, structure sensitivity curve. Another area of concern is does the alumina in the does the non-framework alumina contribute to selectivity or to activity at all? In other words, what it looks like is that the framework that people had suggested, or we had thought, for example, that maybe the non-framework alumina was involved in, say, octane or some other things, based on the work that we just saw, that it looks like the framework is basically responsible for the activity and selectivity that we see in USY. Then the question is there anything, does the non-framework alumina do anything? So we spent some time trying to identify these things. There's been 4 different kinds of non-framework alumina that have been identified. There's tetrahedral, there's a pentacoordinate that's been suggested that it's possibly a distorted tetrahedral, which seems unreasonable. There's also an octahedral form. This shows those 3 peaks. This is a steam deilluminated clay, a metakaolin in the top. In the middle is a silica alumina cogel, 40% alumina, and in the bottom is faujasite. And the fact is that almost any silica alumina material that you subject to some hydrothermal treatment will give you all 3 of those peaks. This is andalusite, which is known to contain pentacoordinate aluminas. We run it at 2 different, at 600 megahertz and 500, and also previously at 400. Here, this shows at 6 and 500. There is some shift in the case of andalusite, although not very much, which means that there's not a tremendous distortion. In the faujasite sample, the pentacoordinate peak shifts hardly at all, which would contradict the assignment of an attempt to assign it as a distorted tetrahedral peak. This is HCSM5, and one of the things that's interesting about this, as we've seen with other things, is that you need a high spinning rate. The pentacoordinate alumina requires a very high spinning rate. And as you spin faster and faster, you'll see more and more peak at about 30 parts per million. We spent some time trying to see these things, and it turns out that there are spinners that contain small amounts of alumina. Torlon is one of them. If you use one of those spinners, you don't get a very good spectrum. So you have to run the empty spinner, because even a very small signal like the top can completely distort, say, the spectra of ZSM5 or of faujasite or anything else you're trying to run, especially low alumina containing zeolites. It is possible to wash out this non-framework alumina with either by a caustic followed by an acid treatment or by an acid treatment by itself. We're not sure if the caustic does anything at this point, but it seems to. When you do that, you see something very interesting. For example, the top spectra is the unwashed material. The bottom spectra is after washing. On the right, there's the aluminum spectra, and of course all the non-framework alumina goes away. This is a Davison type USY after washing, before and after washing. All of the non-framework alumina goes away. The other interesting thing is that the silicon spectrum, when you wash it, you begin to get a bigger peak for silicons with one aluminum, which is what and it becomes pretty much what you expect that cell size. In fact, in the top case, by NMR, you don't get the right silicon ratio. If you try to analyze that NMR, you don't get the right silicon-aluminum ratio. The bottom spectra, you do get the correct chemical silicon-aluminum ratio. And what that means is that the aluminum that is in there after hydrothermal dealumination is in some way coordinated to the framework, occupies exchange sites, coordination sites, something of that sort, which affects the silicon spectrum. If you very severely hydrothermally deilluminate something, you see something very interesting, which Cormo reported about a year ago. And you see a shoulder that occurs on the 60 ppm framework aluminum peak. And this shoulder is at about 55 or 54 ppm, which is where amorphous tetrahedral aluminum appears. And you see it both in silicon hexafluorodeilluminated samples and hydrothermally deilluminated samples. And furthermore, it doesn't wash out. In the case of the spectrum on the right, we did the acid caustic treatment, and it doesn't come out. That particular material, in fact, if anything, is enhanced. So it's different. To find out if some of these non-framework aluminas affect selectivity, we ran selectivities before and after washing and activities, and frankly, there's nothing. We see no effects whatsoever. That does not mean that the peak that Cormo in Spain has identified does not have anything to do with it. It's not related to selectivity because that doesn't wash out. So what we've shown is that octahedral and pentacoordinate alumina are apparently unrelated to either activity or selectivity. The tetrahedral non-framework alumina, we don't know because we can't remove it. The ability to wash out the non-framework alumina allows you to correlate the number of aluminums per unit cell with the unit cell size. Brecken and Flanagan did that a long time ago with a range, say, between 24, 60 unit cell on up onto the X region. And people have wondered whether or not the Breck-Flanagan relationship extrapolates down into the USY and into the 2430 and 2420 unit cell size. So based on the washing scheme, we got some data points. Jack Lunsford had done something like this using NMR, silicon NMR, and he had gotten something quite different from the Breck-Flanagan relationship. The results that we have essentially confirmed that Breck-Flanagan is good down to, ours is slightly different, but within the error of what we have is essentially the same as Breck-Flanagan. Since we had identified, we feel that we had identified octane as being involved with hydrogen transfer, we thought that we would do some hydrogen transfer using a pure cyclohexene reaction that was first done by my French isn't very good, by the Magno, Gallet, Wisne, I hope that's right. They were using a very interesting reaction. The idea of what you do is, you run that reaction, and the cyclohexane will go to the cyclohexene will go to isomers, cyclohexene isomers, or it will hydrogenate to cyclohexane, and then it will also go to for example, methylcyclopentane isomers of methylcyclohexane. So you can look at isomerization, which ought to be a measure of total acid strength, and you can look at hydrogen transfer ratio, hydrogen transfer reaction, which should be a measure of basically the binary site density, and you can compare that ratio. And so we can get relative rates of isomerization and hydrogen transfer. And when we do that, we get experimentally something very similar to the octane curve, which is what we expected. And we also get something, again, similar to that ratio of sites to binary sites, to that structure sensitivity. And again, if we correct that thing for that factor of site strength, isolated to binary site strength, again, we get a little better, still we be even better. We're still collecting data. This is, for example, what you get if you run cyclohexene over 3 different catalysts. In this case, a rare USY, relatively high cell size, a beta, and a ZSM5, and these are all run at about 23 to 1 silica alumina ratio. They all have the same, essentially, they have the same silica alumina ratio. And this is the activity for hydrogen transfer for these catalysts. And what you can see is pretty much what you might think is that the REUSY is the highest, and the beta and the ZSM5 are not nearly as good in hydrogen transfer. An extremely interesting result is if you look at methyl cyclopentane, there is a fundamental difference between the beta and the ZSM5 and the REUSY. The curves for beta and for ZSM5 go essentially through the origin. And what that means is Kormo and Wojciechowski have developed a terminology which is suggested. They would call that a primary stable product. That means that it's formed initially and it's not a secondary product. And furthermore, it doesn't quickly disappear and go to something else. For reasons that aren't obvious, what that implies is that methyl cyclopentane can be formed directly from methyl cyclohexene over beta or ZSM5, but not over faujasite. So there's some fundamental difference in those, in the basic mechanisms involved over those otherwise similar silica alumina materials. You can also look at the isomerization, olefin isomerization, and the paraffin isomerization over, say, experimental distributions. It turns out that all of the catalysts, beta, USY, they all give essentially experimental to the same distributions, and they are experimentally the distributions that you would expect thermodynamically, as long as you use the original thermodynamic tables that were published in 1946 by Kirkpatrick and Frozen and Pitzer, and do not use any of the new compilations, including Stulls, Rossinis, or Albertis. The paraffins are a little more interesting. Again, what we're seeing is that USY simply is not very good at isomerizing paraffins. We do not get thermodynamic ratios. Beta, we do begin to get close to thermodynamic ratios. That's been interpreted by Whitecamp and some other people as shape selectivity, but I really don't think so. I think there's some fundamentally different mechanism going on in this case. Conclusions are that we feel that activity and selectivity is dominated basically by framework aluminum and materials. We feel that there is an avoidance rule. It's not exactly the one that Dempsey had suggested. You can, in any event, you can have 2 kinds of framework sites in USY, isolated and binary. Octane is essentially a structure sensitivity type selectivity. Non-framework octahedral and pentacoordinate alumina does not contribute significantly. Tetrahedral framework alumina is interesting. Use aluminum-free spinners if you're going to do NMR experiments. There are interesting differences in structure that can change in odd ways in some of these zeolite mechanisms. Finally, I'd like to thank John Gano and Mark Wadsworth and Mark Pieters Colorado State Regional NMR Center and the Smithsonian Institution for their sample images. Thank you very much. Actually, have a minute or two for questions. Yes?
Why is there a difference between in that case?
It's a good question. Do you know? I would be very, I'm interested in that, to be honest with you.
Especially if it's more recent ones would be better.
Well, you might, except that unless they're simply copied from the literature, and there's some, or unless somebody has gone over the literature and has got some kind of program, smoothing program or something that interpolates. I don't know. It's interesting. I mean, I think that the ISO, I think that the C5 olefin ratios and the C6 olefin ratios in the modern compilations are not very good. I think there's some errors in some of those tables. Yes.
Well, you showed octane number enhancement. You did not show activity. Was there a reason for not showing it?
Well, those octanes, what people do is that they interpolate. In other words, those octanes will all contain the same activity.
No, but I mean, if you plot activity versus the binary and the isolated, what kind of conversions do you get?
The activity per site, we're doing that now. I mean, the thing is that what you need is to get an activity per site, and people who worked on that with CSM5, and they thought they had something, and they worked on it with faujasite, and faujasite is very difficult, and it's not obvious how that works. Now, I guess what you're suggesting is that with that correction, we might be, with that, knowing something about that, we might be able to go through that thing. I guess part of the problem is there's coke and there's other things to get involved. So, yes.
Would you care to speculate on the differences in the selectivity that you're seeing with the cyclohexane?
Could you repeat this question, please? We're not
Okay, he's interested. He was asking me to speculate on why these apparently similar zeolites give very different selectivities for, say, cyclohexene going to methylcyclopentane. Is that correct? And I'll tell you the truth, I don't have the slightest idea. It strikes me as very odd that that should happen.
Did you, your feed for the cyclopentane, is that pure?
Cyclohexene.
I'm sorry, cyclohexane. Is that pure cyclohexane?
We're using it as it comes. It's good. It's not perfect, but it's good. We're using the gold label, whatever that is. But we're not distilling it or anything.
But it's not a small amount and a large amount of inert or something like that?
No. We're using the method of those, of the French. Yes.
Now, I think on the early work on dehydrocyclization and isomerization of cyclohexane, is it possible, I mean, I think it's possible that the isomerization to methylcyclopentene or pentane requires 2 sites. And that might give some significance to binary sites. I wasn't able to think through your data,
Could be.
but it may require 2 close sites.
Could be. It's very possible. Thank you very much.
Thank you, Al. Our second presentation from the Tarrytown, New York, joint paper from Green Carbide, UOP, probably all Green Carbide, by Scott Blackwell, John Beth, H.F. Hillary, T. G. Kuninsky, J.G. Velasquez, and it's entitled Solid State NMR Characterization of Catalyst, Special Emphasis on Zeolite Hydrocracking.